Hi viewers, welcome to Lama Solution. Today we are going to see about neural network MPPT controlled grid connected PV wind battery system, and also it is known as hybrid DC and AC microgrid. This hybrid DC and AC microgrid will be controlled by means of neural network MPPT in wind energy conversion system as well as solar PV system, and DC bus voltage will be controlled by means of voltage control method in the bidirectional converter of the battery, and the current control is applied in the grid side inverter based upon the SOC of the battery and PV power. The current control will be happen in the grid side inverter, and this is a similar model of the neural network MPPT controlled grid connected PV wind battery systems. System consists of a wind energy conversion system. This is a wind turbine and the PMSG, and then this known as rectifier to convert AC to DC, and then here we are using boost converter. So this boost converter is to for extract the maximum power from the this wind energy conversion system. This boost converter going to be controlled by means of neural network. This neural network can be receive two inputs. One is rectifier voltage and the rectifier current. That means here we have to measure the current of the rectifier. Here we are measuring the voltage of the rectifier. That going to be given to the neural network MPPT control. It will be generated duty cycle based upon this rectifier voltage and current. So this is going to be processed via this pendulum generator, the pendulum generator switching pulse, and is going to be controlled this MOSFET now to extract the maximum power from the this wind energy systems. Maximum rating of this wind energy system is around 3 kilowatt, and the output of this boost converter going to be connected to the DC bus. Here we are going to maintain DC bus voltage equal to 400 volt. Next we are going to see about the solar PV energy system. This is solar PV energy system consists of solar PV panel. This solar PV panel rating is 2000 watts. Each panel having that means totally we have a panel connected in series. The single panel rating is 250 watts, and then this panel PV array will be connected to the DC bus via this boost converter. So this boost converter going to be used for extract the maximum power from the PV panel based upon the neural network MPPT algorithm. So in order to generate a duty cycle, the neural network MPPT algorithm receive two inputs. One is PV voltage and current. So based upon PV voltage and current, it going to be generate duty cycle. So this duty cycle again going to be processed by a pendulum generator. The pendulum generator generate the pulse for this IGBT. This pulse going to be controlled this boost converter to extract the maximum power from the PV panel. So next you have to see about the battery energy storage system. Here we are using battery. Battery going to be connected to the DC bus via this bidirectional converter. The operation of bidirectional converters maintain the DC bus voltage at 400 volt. Now to maintain that 400 volt DC bus, this converter will be controlled by means of voltage control method. This is a voltage control method here implemented for that bidirectional DC converter. Here you can see that the bus voltage will be compared with the reference voltage, and then it will be processed via PA controller. The PA controller will be generated in duty cycle. It will be processed via pendulum generator, and then pendulum generator will be generate the pulse. So this pulse will be control this bidirectional converter, these two IGBT, not to maintain the DC bus voltage constant at to 400 volt. Battery going to be charging discharging mode according with the power balance in the system. And here we are using DC load. So DC load to draw DC power from the wind, PV and battery, and it can draw power from the grid based upon the IPV and the SOC. So next you have to see about grid connected inverter and grid. Here we have single disk grid is going to be connected to the inverter via the cell filter to the DC bus. This inverter going to be controlled by means of current control concept. Here we implemented that current control concept. So in order to control this inverter, we need to generate reference current, right? So this reference going to be generated based upon these two conditions. We are going to compare, then we are going to compare the IPV with the 0.5 and the SOC with the 10%. For example, IPV is less than 0.5, it is less than 10%. So there is no power in the PV panel and there is no charge in the battery. So then we are going to get the power from the grid with the peak amplitude of minus 10 amps. If IPV is greater than 0.5 and the SOC at the battery is greater than 10%, then we can send some power to the grid That's why we are sending some power to the grid with the peak amplitude of 2 amps current. Here we have that reference current in the form of DC, that should be converted to the AC. For that we are using this PLL concept in order to generate sine and cosine. It when multiply it within this reference current, and then it's going to be converted it to AC form, right? And then it's going to be converted into DQ by using ABC to DQ transformation. And then here we are going to measure the current, inverter current. So this current going to be converted into DQ form. After converting the DQ form of actual inverter current and the reference current, that going to be processed by a current controller. This current controller going to be generate the control voltage, the form of DQ, and then you're going to be converted into AB form, and then you are taking only AB. So this AB going to be processed via sinusoidal PWM generator. This sinusoidal PWM generator going to be generate the pulse for this inverter to control the current flow. And this inverter going to be act as in bidirectional mode based upon the condition of the IPV and SOC. So this is a model explanation of this neural network MPPT controlled with connected PV in battery system. So next you have to test the model. That means here we are providing the wind speed is initially is around 12 meter per second up to 2 seconds. After 2 seconds, wind speed change to 1.8 meter per second. And then here we are fixing the irradiation. So every 0.3 seconds, the irradiation change from 1000 to 500, 500 to 10, and 10 to 500, and then 1000. And here we are fixing the SOC initial C is equal to 50 percentage. Already we simulate this model, we have to check the cells. This is a PV voltage, current, and the PV power. Initially, the PV power is around almost 10 or 2000 watts because it is operated at 1000 watts per meter square. After 0.3 second, irradiation change from 500 watts per meter square. That's why you are getting 1000 watts from the PV. After 0.6 second, the irradiation change to 10 watts per meter square. That's why you are getting power around only 0. She can see that the current variation for different irradiation condition for 1000 watts per meter square, the current is around 8.2 amps. For 500 watts per meter square is around 3.8 amps, and then for 10 watts per meter square current almost 0. So this is a variation of PV voltage for the that means for 1500 watts per meter square, the PV voltage may maintain around 245 or 246 volts. Because of this variation, and then we can see the power of wind energy conversion rectifier and boost converter. Here you can see that for 12 meter per second, the power almost maintained up to 2700 watts. For 10.8 meter per second, the power is maintained around 1500 watts. Because of these changes, right, you can see the variation of battery. Here you can see that battery current variations. Initially, you can see that there's a variation due to PV power variation because of change in irradiation. After 2 seconds, you can see that there is decreasing charging current of the battery. This is because of change in speed of the wind. And you can see this is a DC bus voltage, a DC load current, DC load power. So here you can see that the DC load power maintained constant at around 1000 watts. Here you can see that the DC bus voltage maintained at around 400 volt and DC load current maintained at around 2.5 amps. This is a inverter voltage and current. So I'm going to expand this one. Here you can see that inverter voltage maintained at 230 volt, and then the inverter current is maintained at 2 amps peak, because you can see that the SOC of the battery is 50% each. Here during this time we point from 0.6 to 0.9, right? The PV current goes to less than 0.5, but the SOC of the battery is maintained go 50% only. That's why that condition, that means we are not yet taking any current from the grid. So we are sending current to the grid only. That's why inverter current amps will be maintained at 2 amps peak. And you can check the phase angle, right? Both are in phase. In phase means and DC microgrid sending power to the AC grid. It's a concept. Now I'm going to change the same system. I'm going to make the SOC of the battery in percentage, right? So we can see the result at time of 0.6 seconds. So what will be happen? The PV current will be go to less than 0.5 seconds, less than 0.5 amps, and also SOC of the battery is maintained at less than 10%. We will check the detail whether we are getting power from the grid or not during that condition. Now battery charging condition. Now grid is taking power from the AC grid, taking power from the DC microgrid. That's why it's maintained at 2 amps peak. Here you can see that the PV cover is maintained at 2000 watts because of irradiation equal to 1000 watts per meter square. After 0.3 seconds, the irradiation changed to 500. watts per meter square. Because of that, you can see that the PV power goes to 1000, nearly 1000 watts. After 0.6 seconds, is what will happen that PV power goes to zero and that PV current goes to zero. During this condition, definitely the IPV is less than zero point 0.5 and SOC is less than 10 percentage. Then the system or DC microgrid should get the power from the AC grid during this condition. So you will check this condition whether it is working or not. Now you can see that during this condition, right, PV current goes to less than 0.5 and SOC is less than 10 percentage. Battery goes to charging mode only. Here you can see that the change of current, right? Inverter current change from 2 amps peak to 10 amps peak, and you can see the phase angle difference between voltage and current, right? Both are in a opposite each other. What's the meaning? Now we are getting power from the AC grid to DC microgrid. So this is the reason the phase angle between this voltage and current is 180-degree apart. So what's the meaning? We are getting power from the AC grid in order to charge the battery as well as supply the DC load. For this condition, the system work well. We are getting power from the grid during this condition. That means when IPV is less than zero point 0.5 amps and then SOC is less than 10 percentage. System work well during this condition. This is working of the neural network LDPT, and you can see that maximum power extraction from the PV is almost meeting at the peak power on all the irradiation condition, and you can see that the power of P that been wind maintained at the maximum power point in all operating condition. During this all variation of irradiation and with speed condition, we are getting maximum power from the solar PV as well as wind energy system. By using that neural network MPPT, the system will work for all kind of operating condition. This is working of this model. Thanks for watching our videos. Kindly subscribe our channel and click bell icon for notification about upcoming video. Thank you so much. Bye bye.